Large language models are powerful, but they become truly transformative when we build agents around them. This blueprint lays out the core architecture that turns a static LLM into an autonomous agent capable of reasoning, acting, and learning from its environment. What changes when an LLM becomes an agent? Start with the boundary, what an LLM can do alone. A standalone LLM is, at its core, a text generator. It receives a prompt, produces a response, and then stops. That may sound limiting, but the limitation is precisely what makes the boundary so useful. The model does not continue on its own, does not persist intent between turns unless some external system preserves that intent, and it does not inspect the world unless a surrounding application supplies evidence. In operational terms, the model is reactive. It answers the current input, but it does not possess an execution loop that can change the next step based on what happened before. It can simulate deliberation in language, but simulation is not the same as an actual process that can inspect results, decide again, and take the next action. This distinction matters because many modern products wrap an LLM in enough surrounding machinery that the whole system appears agentic even when the model itself remains a one-shot responder. A chat interface, for example, can feel interactive and even smart while still behaving like a sequence of isolated generations. Each term may be informed by prior messages, but if no component can initiate tool use, branch execution, or continue after observing a result, the system is still just a dialogue application. The model is being used to produce text within a conversation, not to operate over a task loop. Figure 1.2. A standalone LLM is a one-shot responder. An agentic system adds orchestration, tools, and feedback-driven control flow. The easiest way to see the gap is to compare a question-and-answer interaction with a task that needs exploration, verification, and action. If Atlas Travel Assistant is asked, what is the fastest way to get from Boston to Chicago next Friday? A plain LLM can produce a plausible answer from prior knowledge or from the information visible in the prompt. But that answer is only as good as the model's internal recall and whatever context was included. A truly agentic system can notice that the task requires live data, decide to search flights, compare constraints such as price or departure window, and then revise its recommendation based on the retrieved results. The difference is not elegance of wording. It is whether the system can move beyond a single response into a sequence of informed actions. A useful mental shortcut is that a plain LLM speaks, while an agent does work. Speaking is not trivial, but it is not the same as acting. Work requires an environment, a way to inspect that environment, a way to choose among actions, and a way to learn from the result of those actions. That is why the term agent should not be reserved for any product with a model attached to it. If the surrounding application never lets the model influence the next step beyond filling in text, then the model is a component inside a workflow, not the controlling intelligence of an agentic system. A working definition of an agentic LLM system. An LLM becomes agentic when it is embedded in a control loop that lets it reason about a goal, act through tools, observe feedback, and decide what to do next. The operational definition is intentionally system-centric. It does not depend on model size, benchmark score, or the apparent fluency of the output. A small model with the right loop can behave more agentically than a larger model locked inside a one-shot prompt. What changes is the runtime behavior of the system, not the intrinsic nature of the model weights. Figure 1.1. The agentic LLM loop. A goal-driven cycle of reasoning, tool use, observation, and repeated decision-making. That definition has a practical consequence. Agency is not a property of language generation alone, but of the surrounding execution pattern. The model may propose a plan, but the system must be able to carry that plan into an action space outside the model. The model may inspect a tool result, but the system must be structured so that the result can influence the next decision. The model may say, "I will check the weather and then decide." But unless there's an actual mechanism for checking the weather and feeding that result back into the next turn, the system is only narrating agency, not implementing it. The reason this operational framing is so important is that it prevents a common category error, treating impressive language as evidence of effective autonomy. A model can describe a good strategy without being able to execute it. It can also generate an answer that sounds grounded even when it is unsupported. In an agentic system, the question is always whether the model's outputs have consequences inside a loop. If the answer can trigger search, retrieval, computation, database reads, API requests, or approvals, then the model is participating in a process that extends beyond text completion. Atlas Travel Assistant makes the idea concrete. In a non-agentic setting, Atlas might answer a travel question with a single synthesized recommendation. In an agentic setting, Atlas can separate the task into inspection and action. It can search for live options, compare them against constraints, observe that one itinerary exceeds a budget threshold, search again with different parameters, and ask for approval before booking. The same model may generate the text in both cases, but only the second case deserves to be called an agent because the system as a whole can continue deciding after each observation. The reasoning action feedback cycle in practice. The core mechanism of an agentic system is a repeated cycle of reasoning, action, and feedback. Reasoning here means selecting what should happen next given the current goal and the current state of the task. Action means doing something outside the model, usually through a tool. Feedback means observing the result of that action and using it to shape the next decision. The cycle is not merely a philosophical loop. It is an execution pattern that makes behavior path-dependent. Every result can change the information available for the next step, which means the system's future behavior depends on what it has already done. This path dependence is what makes agents powerful and, at the same time, more difficult to reason about than ordinary prompt response applications. A single-turn model call is easy to inspect because the output depends only on the prompt and the model's internal state at that moment. An agentic loop, by contrast, accumulates consequences. If Atlas searches the web and discovers that a preferred train is sold out, that fact changes the next action. If a calculation shows that a route violates the budget, the agent may branch into a cheaper alternative. If a tool call fails, the failure itself becomes feedback and may trigger a retry, a fallback, or escalation to a human. In each case, the loop turns the model from a generator of answers into a participant in an evolving process. The practical value of the cycle becomes obvious when the task requires uncertainty management. A travel assistant is rarely asked for a purely static fact. It must often compare multiple options, account for changing availability, and interpret incomplete constraints. A one-shot answer can only approximate this work. An agent can revisit its own assumptions after each observation. That matters because the environment may not cooperate with the original plan. The best option at the start of the task may disappear halfway through, and the agent must be able to adapt without pretending that the world is fixed. The cycle also makes explicit something that is hidden in many non-agentic systems. The model does not need to know everything up front if it can observe enough along the way. This is one reason tool used changes the shape of the problem. Instead of loading every possible fact into the prompt, the system can defer some knowledge acquisition to runtime. That creates a cleaner separation between interpretation and inspection. The model decides what information it needs, the tools gather that information, and the next turn uses the result. The intelligence is therefore distributed across the loop rather than compressed into a single generation. Why tools matter more than prompts. Tools are the capability boundary that turns a language model into an operative system. A prompt can ask the model to think carefully, but it cannot make the model reach outside its own weights. A tool can. That is why tool access is so central to agent design. It externalizes perception, computation, and action. Once a model can call tools, It no longer has to fake access to the world through language alone. It can inspect current data, perform calculations that are exact rather than approximate, retrieve policies or documents, and even initiate external actions when policy permits. These tools are not all the same, and the distinctions matter. Retrieval tools let the agent look up information that should not be memorized or may have changed since training. Search tools widen the agent's observational field beyond internal knowledge, which is crucial when the task depends on live or domain-specific facts. Computation tools give the agent precise arithmetic, date handling, ranking, or optimization capabilities that language generation alone cannot guarantee. Action tools go further by affecting external systems, such as sending a message, creating a booking, updating a record, or initiating a workflow. Each category changes the failure mode profile in a different way. Retrieval primarily improves grounding. Computation improves correctness, and action creates side effects that must be governed carefully. It is tempting to blur these together under the vague idea that the model has tools, but the production consequences are different. A retrieval tool reduces hallucination risk for factual content, yet it does not, by itself, make the system capable of doing work. A calculation tool can produce trustworthy totals, yet does not grant any operational authority. An action tool can make the system useful, but it also introduces real-world consequences and therefore demands scope limits, confirmation steps, and auditability. An agent is not simply a model plus utilities. It is a loop in which those utilities are selected and sequenced by the model under constraints. Atlas illustrates the progression well. Without tools, Atlas can only answer from prior knowledge or from the text already provided. With search and retrieval, Atlas can collect live flight options and hotel policies. With computation, it can compare total cost, elapsed travel time, or cancellation risk in a reliable way. With action tools, it can reserve a seat or draft a booking request. The important point is not that every agent should have every tool. The important point is that once a tool exists, the model can delegate part of the task to the environment and use the returned result to shape the next move. From assistance to action, informing a reply versus doing work. There is a deep difference between using a tool to inform an answer and using a tool to produce a durable change. The first is still a conversational act. The second is operational. If Atlas queries a travel site and then writes, "The best available flight appears to be X," the tool has only supported the reply. If Atlas then creates a tentative booking, updates a trip record, or sends an approval request, the tool has changed the state of an external system. Those are not just different levels of sophistication. They imply different reliability requirements, different observability expectations, and different governance rules. This is why not every tool-using application should be called an agent in the same sense. Some systems remain closer to assisted generation. They retrieve documents, summarize them, and produce a response. That can be extremely valuable, but it is still fundamentally answer production. Agentic systems go further by allowing a tool result to alter subsequent execution and, in some cases, to create durable effects outside the model. In practice, this distinction often determines whether a product can be shipped as a helpful assistant or must be treated as an operational actor with explicit controls. The distinction also shapes user trust. A system that only informs a reply can be evaluated like a better search and summarize experience. A system that can take action must be trustworthy in the stronger sense that it respects constraints, understands when it is uncertain, and knows when to pause. If Atlas recommends a hotel based on current inventory, users may tolerate ordinary answer errors. If Atlas submits a booking on the wrong dates, the error is no longer cosmetic. The line between answer and action is therefore not semantic overhead. It is the line between informational assistance and material side effects. This is one reason production agent design often starts by asking not what can the model say, but what can the system do and under what conditions. That framing forces clarity about tool boundaries. Some tools should be read-only. Some should be restricted to drafts or simulations. Some should require approval before execution. The more the system can do, the more explicitly its effects must be constrained. That is not a weakness of agents. It is the operational condition that makes them safe enough to deploy. Bounded autonomy as the deployment constraint. Bounded autonomy is the idea that an agent should be free enough to be useful and constrained enough to be safe, reliable, and governable. This is not a philosophical compromise added after the fact. It is the deployment requirement that makes agentic systems possible in the first place. A completely unconstrained agent would be too risky to trust with real tasks. A completely constrained system would collapse back into a rigid workflow and lose the adaptive behavior that makes agents valuable. The design problem is therefore to find the right envelope of freedom. In practical terms, that envelope is defined by permissions, scope, and allowed actions. Permissions determine which tools the agent may call. Scope determines which tasks it is allowed to attempt. Allowed actions determine what kinds of side effects it may produce without additional review. A travel assistant might be allowed to search, compare, and draft booking options, but not to finalize payment without approval. It might be allowed to use only approved vendors. It might be limited to a single trip thread and prevented from making unrelated changes to the user's profile. These limits are not bolt-on safety measures. They are part of the operational contract of the agent. Bounded autonomy also includes ceilings on how long the loop may continue and how far it may branch. An agent that can reason forever is not practical. An agent that can explore every possible route is not affordable. An agent that can make arbitrary decisions outside its intended domain is not trustworthy. Real systems therefore need guardrails on step count, tool budget, time budget, data access, and escalation thresholds. Those constraints may feel restrictive in a laboratory setting, but in production, they're what make the system dependable enough to run repeatedly without human supervision at every turn. The product lens is useful here. Shipping an agent is mostly the art of deciding what it may not do. That sounds less glamorous than unrestricted autonomy, but it is the difference between a demo and a system. A travel assistant that can research cheap flights but cannot overbook, alter unrelated reservations, or ignore approval thresholds is far more deployable than a hypothetically omnipotent assistant that can do everything and therefore must be trusted with too much. Bounded autonomy is the mechanism by which capability becomes service rather than liability. Agent versus workflow, where the model decides. The easiest way to confuse an agent with a workflow is to look only at the presence of an LLM. A workflow can contain a model call and still not be an agent. In a workflow, the broad structure is predetermined. The system may branch, but the branches are usually explicit and designed by the developer. The model fills in content at certain points, but it does not meaningfully choose the execution path. In an agent, by contrast, the model participates in deciding what should happen next. That decision can still be constrained, but it is a real decision rather than a slot-filling step. This distinction is subtle but crucial. A script that says first classify, then retrieve, then summarize is a workflow. It may be intelligent, and it may use an LLM in one or more steps, but its control flow is fixed. An agent might begin with the same classifier, but if the retrieved evidence is insufficient, it can choose to search again, ask a clarifying question, route to a different tool, or request approval. The model is therefore not just producing outputs within a pipeline. It is participating in path selection under conditions that cannot be fully enumerated in advance. This is the point at which many people unintentionally misuse the word agent. A retrieval-augmented generation pipeline may feel agentic because it augments the model with external knowledge. Yet if the model always receives a fixed retrieved bundle and emits a summary, it is still a retrieval pipeline. Likewise, an ordinary API wrapper may appear smart because it exposes model outputs through a product interface. But if the wrapper never allows the model to continue acting, it is not an agent. The model has been embedded in an application, not granted control of a loop. For Atlas, the difference is visible in behavior. If Atlas merely formats hotel search results into a polished recommendation, it is part of a workflow. If Atlas can decide that the results are too sparse, change the query, compare alternatives, and pause for approval before booking, then the model is influencing the next step and the system is behaving agentically. That distinction will become even sharper once state and control flow are formalized, but the principle is already visible here. Where the model decides, agency begins. Common misclassifications and why they matter. Chat interfaces are often mistaken for agents because they feel conversational. The problem is that conversation alone is not agency. A chat UI may preserve message history and may even call tools behind the scenes, but if it does not embody a task loop with decision points, it remains an interface around a model. The model is responding to prompts in sequence, not actively managing a bounded objective. This distinction matters because teams frequently overestimate autonomy when the user experience is smooth and underinvest in the control mechanisms that true agency requires. Retrieval pipelines are another frequent source of confusion. They can be impressive, especially when they produce well-grounded answers from a corporate knowledge base or a live index. But retrieval is still a support function unless the system can alter its own next action based on what it retrieved. If the retrieved documents always flow into a fixed summarization step, the architecture is not agentic. It is a strong answering system that is useful, but it should not be designed, tested, or governed as if it can reason through open-ended operational choices. Scripted automations can also masquerade as agents when an LLM is used as a component inside them. A script may call a model to classify a request, then route to a predefined handler. The LLM may appear to decide, but often it is only selecting among a narrow, developer-defined menu. That could be a perfectly sound design, especially when reliability matters more than flexibility. The danger is in calling it an agent without recognizing the limits. If the system cannot depart from its scripted path except in ways already anticipated by the developer, then it is better described as an orchestrated workflow. These distinctions are not pedantic. They affect evaluation, monitoring, and user expectations. If a system is really a workflow, then failures are often about routing logic, prompt quality, or integration bugs. If it is an agent, failures include bad decisions, unnecessary tool calls, missed feedback, and unsafe action selection. Using the wrong label leads teams to apply the wrong controls. The whole point of this chapter is to build a vocabulary that matches the runtime behavior, not the marketing copy. A brief bridge to multi-agent systems. Once a single agent loop becomes too narrow for the task, teams often decompose the problem into multiple cooperating components. That is the basic idea behind a multi-agent system. One component may research, another may draft, another may verify, and a coordinator may route work among them. This pattern is especially attractive when the problem has separable subskills or when different policies apply to different parts of the task. In that sense, multi-agent systems are a scaling strategy for complexity, not the default definition of agenthood. It is important not to let the multi-agent idea obscure the base unit. Every multi-agent system is still built out of single-agent loops, even if some of those loops are narrow or highly specialized. A supervisor-style setup simply coordinates them. That means the conceptual foundation remains the same, a loop that reasons, acts, and observes feedback under constraints. The added layer is coordination, not a different species of intelligence. For Atlas Travel Assistant, a multi-agent version might split research, budgeting, and booking into separate specialists. That can improve modularity and clarity, but it is not required for the system to count as an agent. The single-agent loop is the more fundamental abstraction, and it is the one you need to understand first. Once that is clear, multi-agent designs become an extension of the same logic rather than a new philosophical category. Atlas Travel Assistant as a running example. Atlas makes the whole distinction concrete because travel planning naturally demands iteration. A user starts with a goal that is often underspecified. Find a workable itinerary, keep the budget reasonable, respect dates and preferences, and perhaps hold off on final booking until the user confirms. A standalone LLM can generate a polished answer from whatever it knows. An agentic atlas can do more. It can search for current options, notice which constraints are binding, compare alternatives, and revise its plan after each observation. The system is no longer merely responding to the question. It is actively reducing uncertainty around the task. Suppose Atlas is asked to plan a weekend trip from San Francisco to Seattle. In a text-only mode, it may produce a plausible itinerary and a generic hotel suggestion. In agentic mode, It can inspect live availability, check whether the traveler's preferred departure time is still open, compare total cost across carriers, and verify whether the hotel is within walking distance of the destination. The feedback from each tool call changes what Atlas should do next. If flights are too expensive, it can shift the search window. If the hotel is unavailable, it can search a nearby district. If the itinerary passes the user's comfort threshold, it can prepare a booking draft and wait for approval. The important nuance is that Atlas does not become agentic because it talks about these steps. It becomes agentic because the runtime allows those steps to happen in sequence, with each result influencing the next turn. The model's internal capability has not changed, the surrounding system has. That is why the rest of the chapter will shift from conceptual language to control flow, state, and explicit transitions. Once you can see the difference between a model that speaks and a system that acts, the need for formal orchestration becomes obvious, and the next abstraction naturally becomes stateful control rather than ad hoc prompting. Control flow structures, conditionals, loops, and function calls form a substrate on which intelligent agents are built. Understanding how these primitives compose is essential before we layer on perception, memory, or planning. An agent's behavior becomes predictable and manageable only when there is a clear structure that governs what it does next. This section explains why that structure, the control substrate, is essential for building reliable agent systems. That informal description, just let the model talk until it seems finished, collapses everything important into an opaque blob. You lose track of what the system knows right now, what it is allowed to do next, what happens after a tool result arrives, when it must stop, and how a human can interrupt without losing progress. Once a system can branch, retry, pause, or resume, the real unit of design is no longer the prompt alone. It is the control structure that determines how the prompt is used, when tool calls are permitted, and how execution moves from one mode to another. A plain chat interface may appear agentic if it can call a tool, but if the tool usage is hidden inside an implicit loop, the behavior is still hard to test, hard to resume, and hard to explain. When you need a bounded travel assistant like Atlas to research flights, compare options, ask for approval before booking, and then continue from a save point after a pause, you need a representation of the process itself. That process must expose its current mode, its allowed next moves, and the policy that selects among them. Without that substrate, the system is not being orchestrated, it is improvising. In a graph-shaped control system, the model may decide what to say or which tool to use, but the control plane decides whether the decision is admissible, whether the workflow should advance, and whether the run should end or pause. That separation is what makes bounded autonomy possible. The agent is free only inside a corridor of explicitly defined transitions. Outside the corridor, it cannot silently drift into unsafe or unbounded behavior because the substrate itself refuses to describe such a path. A prompt that says if you need more information, search the web does not create a deterministic search step. A tool call embedded in free-form text does not create a state transition. An execution log is not a control model. The substrate is what turns a sequence of decisions into an inspectable machine. Many prototype failures come from treating intelligence and motion as if they were the same thing. This diagram shows the two layers clearly. On one side, the model generates candidate content, inference, summarization, ranking. On the other side, the control plane governs sequencing, branching, persistence, and termination. Notice how the control plane wraps around the model's output, deciding what happens next. That separation is what makes the system inspectable and safe. The finite state machine gives us the most compact formal language for describing agent behavior. By the end of this part, you will see how states, events, guards, actions, and termination map directly onto the decisions an agent makes at runtime. A state is not the entire conversation history or every past tool result. It is the smallest piece of information the system needs to decide what to do next. If the agent is in a planned state, it should produce an outline. In act, it calls a tool. In reflect, it evaluates and decides whether to stop. The purpose of state is decision relevance, not archival completeness. Events are what drive the machine forward. A user message, a tool result, a human approval, or a subtask completing. A guard is the predicate that checks whether a particular transition is allowed. An action is the work done along that transition, like appending a message or invoking a tool. Termination is the explicit condition that says the workflow is done. So state is the mode, event is the observable change, guard is the branch predicate, action is the work, and termination is the declared end condition. This vocabulary matters because it prevents a common mistake in agent discussions. People often say the agent reasoned or decided when really a transition fire because a guard evaluated to true. That distinction is not pedantic. It tells you where to look for failures. A wrong tool call points to the action. A wrong branch points to the guard. An endless loop points to the termination condition or a missing transition into the end state. Good control flow makes these failure modes separable. The practical value is that it forces you to describe the agent as a machine instead of a mood. A bounded workflow becomes a finite set of modes with explicit legal moves between them. That means you can test state by state, log and replay transition decisions, and review policy independently of the model's generated text. For Atlas, that is the difference between saying the assistant seemed to keep researching and the assistant was in the research state, received a tool result, passed the guard for remaining uncertainty, and transitioned into comparison. The second statement is operational. The first is anecdotal. State, history, and memory sound similar, but they serve very different roles in an agent system. Let's draw a sharp line between them so the rest of the design stays clean. Runtime state is the compact object the workflow reads to decide what to do next. Conversation history is the full log of every message exchanged. Memory holds information meant to persist across sessions. These three can overlap in content, but they are not interchangeable. A state object might hold a summary of recent messages, a routing hint, or a progress marker. It should not need to store every token ever produced. In agent systems, the control plane needs a small, stable interface. If every decision depends on scanning the full raw transcript, the workflow becomes bulky and fragile. A minimal state schema acts like an instrument panel. It shows the signals needed to steer the next move without replacing the full record. For a travel agent, that might mean storing the destination, current trip stage, and a compact list of recent messages rather than every conversation turn in full detail. A common mistake is letting conversation history masquerade as state. History is valuable for retrieval and auditing, but it should not determine the next transition. A state machine should not scan an entire transcript just to decide whether to continue planning or stop. Memory is for persistence across sessions. State is for what to do next. A checkpoint says where execution was paused so it can resume later. Each solves a different problem. Keeping runtime state minimal also improves reliability. Smaller state surfaces are easier to serialize, validate, compare, and version. They reduce the chance that a node accidentally depends on a field that only sometimes exists. In graph-based orchestration, that discipline is the difference between a reproducible control structure and a tangled accumulator of accidental dependencies. The more precisely the state object describes current control, the easier it is to reason about what the workflow could do next, especially when resuming from a checkpoint. A finite state machine becomes much easier to understand when you remove hierarchy and focus on a single, bounded workflow. This section shows how flat FSM gives you visible control logic that can be tested, audited, and terminated cleanly. Imagine Atlas being asked to plan a weekend trip. A flat machine might start in an entry state, then move into planning, then research, then comparison, then into approval if the booking is sensitive, and finally into done. Each state is a mode that only allows a limited set of next states. The machine does not wander. It follows explicit rules. That simplicity is intentional. If a task is a clearly bounded life cycle, a finite machine is often enough to describe it completely. What makes this representation useful is not that the workflow is short, but that it is bounded. There is a finite set of legal states and a finite set of legal transitions. There is a clean termination condition, and every step can be explained as a move from one named state to another. In the Atlas example, the planning state may produce a short list. The research state may fetch travel options. The comparison state may synthesize trade-offs, and the stop state may emit the final response or await human approval. The machine is finite because the control surface is disciplined, not because the problem is trivial. That discipline pays off immediately in testing. A static prompt may produce an acceptable answer today and a different style of answer tomorrow with no obvious reason. A flat FSM gives you a visible path. You can test the transition out of planning when the trip dates are complete, test the transition into approval when the booking cost exceeds a threshold, and test the transition into stop when a user explicitly declines further action. The machine has a topology, and that topology can be replayed. When a system must be audited after a failure, the question is no longer what did the model feel like doing, but which state was active, which guard fired, and which transition was taken. The other benefit is that bounded workflows force explicit termination. In an uncontrolled loop, stopping can become an emergent behavior based on prompt instructions, token limits, or accidental satisfaction. In a machine, termination is a first-class state or terminal condition. That matters for resource control and for user expectations. Atlas should not continue thinking after it has already assembled the itinerary, nor should it keep cycling because a prompt's said to be thorough. The end condition is part of the design. The agent can still be intelligent inside the machine, but the machine itself knows when enough is enough. A flat FSM is therefore a good baseline, not because it captures every complex agent, but because it makes the control logic visible. Once a workflow is represented as named modes and transitions, the rest of the design conversation becomes concrete. Where should the graph pause? Which states require human review? Which transitions are safe to repeat? Which paths are terminal? Those are questions an engineer can answer. They are much harder to answer when the system is described only as an LLM with tools. Transitions connect states, but guards decide which transition actually fires. A guard is a predicate over the current state and the latest event. It makes routing visible and testable, instead of hiding decisions inside prompt text. A guard checks conditions like whether enough information has been gathered to move to comparison or whether the user has sent an explicit stop request. The key point is that the decision lives in a visible, inspectable place, not buried inside a prompt paragraph where it's hard to test. Actions generate content, call tools, update fields, or append messages. Guards look at the current state and choose among available paths. Keeping these responsibilities separate is one of the most important habits in agent systems. Centralized policy makes routing deterministic, inspectable, and easy to adjust. Determinism does not mean the model output is identical every time. It means the branch decision is a reproducible function of the state and event. That makes the control layer auditable. If a workflow continues past a stop signal, you can inspect the guard in the state that reached it. A guard should usually inspect state that is already known or derived, not perform hidden side effects. If the decision requires a fresh tool call, that tool call belongs in the action layer. Otherwise, the routing logic becomes non-local and harder to reason about. This separation keeps the control plane clean enough to debug from traces and state snapshots. Flat state machines are explicit and easy to understand at small scale, but they do not scale gracefully. As the workflow grows, the number of transitions can explode, and the same logic gets duplicated across many edges. This part explains why that happens and what it costs. The problem is not just having more states. Each new state can add transitions to every other state that matters, and many of those transitions encode the same rule. Imagine a workflow with planning, research, comparison, draft, review, and termination states. The number of possible edges grows quickly. Add a global stop condition, a retry path, and an approval path, and the diagram becomes a dense web of repeated arrows. The maintenance burden comes from duplication. Suppose every state must check whether the user requested a stop. In a flat graph, that logic appears on several transitions. If the policy changes, every one of those transitions must be updated consistently. Miss one, and the machine behaves differently depending on where it was when the signal arrived. The graph becomes brittle because common concerns are repeated instead of factored out. Think of the difference between a flat file list and a folder hierarchy. In one directory, everything is visible at first, but soon naming and repeated patterns become a maintenance issue. A hierarchy lets you put share behavior in one place and inherit it downward. State machines face the same scaling pressure. Flat control works until repeated transitions obscure the actual intent of the workflow. Many developers overreact by assuming complexity needs a smarter prompt. The better answer is usually the opposite. Make the control structure more boring. If a branch is repeated, centralize it. If a policy is global, stop re-encoding it in local text. If a state has internally related substates, nest them. Hierarchy is not a stylistic preference. It is the structural remedy for transition explosion. Hierarchical state machines solve the scaling problem by letting states contain states. A parent superstate represents a coarse mode like working, and nested substates handle the finer-grained steps inside that mode. Instead of representing every local move as a top-level transition, you group the local process into a nested region and let the parent own the broader policy. That reduces duplication and makes the machine easier to read. Common behavior can be shared across a nested region without copying it into every child. A user stop request can be handled by the parent because that is a global policy while the child continues managing local progression from plan to act to reflect. The source code pattern reflects this relationship directly. A shared state schema carries the messages and a marker for the last active substate, which acts as a shallow history pointer. The diagram shows a superstate containing two substates. The parent enforces global overrides, while the child's substates manage internal progression. The history marker lets the machine resume near where it left off. This is a small runtime contract between the parent graph and the subgraph. The messages field carries the recent interaction, while working underscore last records where inside the nested region execution last paused. This is not a full transcript container and not a memory store. It is a small runtime contract between the parent graph and the subgraph. That tiny addition is what makes hierarchy resumable without forcing the machine to replay its own path from the beginning. The subgraph itself shows how a nested region can behave like a machine within a machine. Entry begins at plan, execution advances through substates, and each node updates shared state so that the next decision has a stable basis. Each node returns a new state with a message and updates working underscore last. The subgraph starts at plan, then moves to act. The working underscore last marker expresses shallow history. If the machine re-enters the superstate later, it can know which child was last active. The working underscore last marker is especially important because it expresses shallow history. If the machine re-enters the superstate later, it can know which child was last active and resume near that point rather than pretending the nested region was never visited. A deeper HSM can also contain parallel regions, where separate child regions advance independently inside the same superstate. The central idea remains the same. Hierarchy is about organizing control, not about making the model smarter. Hierarchy lets policy live at the correct level. Local states decide local motion. Parent states enforce global constraints. This separation is what makes orchestration reusable. A parent guard can enforce a universal stop condition or an approval requirement without knowing the details of every child state. A child state can decide whether to proceed to another local state without being burdened by the entire system's rules. Inside the working region, a guard determines whether to move from plan to act or terminate the local sequence. At the parent level, a separate guard inspects recent messages and can shut the whole machine down if it sees a stop signal. The child guard uses the local working underscore last marker to determine the next state within the subgraph. The parent guard ignores those local details and instead inspects the recent message tail for a global termination signal. This creates a layered machine where a higher-level policy can override the default continuation of a lower-level region. This separation is how bounded autonomy is actually enforced in practice. The child guard governs internal progression. The parent guard governs broader continuation. If the same stop condition must be enforced at multiple levels, the parent is the natural place to centralize it. If a subgraph's internal progression should be reusable in another context, keeping its local transitions self-contained prevents the rest of the system from inheriting implementation details it should never need to know. Hierarchical state machines can include parallel regions, independent child regions that advance concurrently under the same parent. This makes control more expressive than a single linear chain of states. Parallel regions are useful when one part of a workflow must continue while another part also progresses, and the parent needs to coordinate their overall life cycle. This is not about multiple agents. It is a control structure capability within a single system. For agent builders, the key distinction is that concurrency and hierarchy are separate concepts. A parallel region is still part of one control system. It does not imply a separate agent with its own goals or negotiation protocol. Keeping that distinction clear prevents confusion with later multi-agent topics. Even without using parallel regions directly, knowing they exist reinforces the central point. The control substrate determines how complicated a workflow can become before it needs to be decomposed. Flat machines solve simple cases. Hierarchical machines handle structured workflows. Parallel regions extend that range, but the basic logic remains. Make control explicit, localize policy, and keep the next transition inspectable. The finite state machine and hierarchical state machine vocabulary maps directly onto the primitives that graph-based agent systems provide. That mapping is what turns formal control theory into runnable orchestration. A shared state schema becomes the common bus through which all nodes communicate. Each node is a stateful control point that consumes state and returns updated state. A subgraph acts as a nested region or superstate with its own internal substates. Conditional edges implement guards by selecting the next node based on the current state, and checkpointing persists progress so execution can pause and resume from a save point. This mapping is more than an analogy. It is the practical bridge from formal control theory to runnable orchestration. When you define a workflow as a graph with explicit modes and guarded transitions, you get a machine that can be inspected, paused, and replayed. The graph framework makes the machine concrete, and that concreteness is what separates a stateless prompt loop from a stateful agent workflow. The minimal code already shows the shape of this correspondence. The state definition is the contract between parent and child regions. The subgraph underscore builder composes nested behavior. The add underscore conditional underscore edges calls in code guarded transitions. The parent graph attaches the subgraph as a node, which is exactly how a superstate delegates to a nested region. Every transition can be named, inspected, and tested. The usefulness of this model becomes clearer when you debug a failed run. With explicit nodes and guards, a trace shows where the machine was, what state it carried, and why it chose its next move. A failure is no longer a vague sense that the assistant went off track. It is a specific branch decision at a specific state with a specific input. That traceability is one of the strongest reasons to adopt a graph substrate early, before the workflow becomes impossible to untangle. The code in front of you is not just a static description of an agent. It is a trace of execution, a set of instructions that define exactly what the machine does at each step. Reading it this way changes how you understand and debug the system. The first code block defines the minimum information the machine needs to continue. The state carries messages because the model needs some conversational substrate to operate on, and it carries a working underscore last marker because nested execution needs a memory of where it left off inside the current superstate. That marker is intentionally compact. It is not a human-readable narrative and not a full log. It is just enough to decide whether the next transition should continue within the working region or terminate. The second block shows how a subgraph behaves like a local machine. Plan underscore node writes a planning message and marks the active substate as plan. Act underscore node writes an action-oriented message and marks the active substate as act. The subgraph starts at plan, which is effectively the entry state of a nested region. The important insight is that each node is not merely producing text. It is mutating the shared control state in a way that changes what the next transition can be. The third block shows two layers of decision-making. Inside the subgraph, route underscore thin underscore working uses the local history marker to decide whether the local machine should move to act or terminate. At the parent level, global underscore guard examines the recent messages and can terminate the entire workflow if a stop signal appears. This gives you a clean example of how local progress and global policy coexist. The child controls local movement. The parent can still override the continuation of the whole region. That is the essence of hierarchical orchestration. The final block adds persistence. A reflect underscore node appends a reflection step. The graph is compiled with a check pointer, and the run is invoked with a thread-scoped configuration. The thread identifier is what lets the execution be associated with a particular live run, so that progress can be resumed instead of recreated. The checkpoint is the saved execution point, not a memory store and not a complete conversation archive. Its job is to preserve progress. Its job is not to remember user preferences for next week. In practice, reading code this way changes how you debug. You stop asking whether the model understood and start asking whether the machine reached the expected state, whether the right guard fired, and whether the checkpoint captured the run at the intended point. That shift is exactly what turns an agent from an opaque prototype into a system whose behavior can be inspected and reasoned about. Checkpointing makes graph execution interruptible by saving enough state to resume from the last durable point. That is what turns a pause into a useful break rather than a lost conversation. A checkpoint is not memory. Memory retains information for future sessions or behavior. A checkpoint only says where the run stopped. The trace records what happened for inspection. The checkpoint is a resumable state artifact the runtime can use to continue. By associating a run with a thread identifier, the system keeps execution paths separate. That matters when the same workflow serves multiple users or exploratory branches. A resumed thread continues its own saved path, while another thread can branch into a different line of reasoning. The checkpoint remembers that progress exists. The shallow history marker helps the workflow know where it last was inside a nested region. Together, they give resumability without reinterpreting the whole transcript. Keeping that boundary crisp avoids a large class of subtle bugs. The checkpoint remembers that progress exists. The shallow history marker helps the workflow know where it last was inside a nested region. Together, they give resumability without reinterpreting the whole transcript. Keeping that boundary crisp avoids a large class of subtle bugs. Graph-based control earns its place through maintainability, not elegance. When a workflow is built from states, guards, and transitions, changing requirements means editing a few explicit edges rather than rewriting prompt cascades and hidden loops. That makes behavior reviewable, testable, and explainable to anyone who needs to understand why the agent acted as it did. The strongest argument for graph-based control is not theoretical elegance. It is that the system stays maintainable as requirements shift. A new requirement typically means changing a small number of explicit edges instead of editing a cascade of prompt text and hidden loop conditions. That makes behavior easier to review, easier to test, and easier to explain to collaborators. A common misreading is to assume that hierarchy automatically improves intelligence. It does not. A hierarchical state machine does not make planning deeper or reasoning better by itself. What it does is organize execution so that complexity is factored into reusable regions and global policy can be enforced cleanly. If the underlying prompting or tool design is poor, hierarchy will not fix it. It will only make the failure easier to locate. Another frequent mistake is to treat history, checkpoint, and memory as if they were interchangeable. History records what happened. A checkpoint records where execution can resume. Memory records what should persist beyond the current run. Mixing them together leads to systems that either forget too much, remember too much, or route based on stale artifacts. A disciplined state machine keeps those layers separate so each one can do its own job. The final lesson is that explicit control flow improves debugging more than it improves style. If a run fails, named states and guards make the failure reproducible from the trace. If a policy changes, the guard logic is visible and can be updated in one place. If a user interrupts the process, the checkpoint tells the runtime where to resume. The substrate does not merely support the agent. It makes the agent legible enough to operate in the real world. From stateless tool use to persistent execution. Why tool access is not yet agency. A model that can call tools is more capable than a model that can only emit text, but that extra capability does not, by itself, turn the system into an agent. Tool binding gives the model a way to request an external action. It does not yet give the host application a persistent execution model, a durable state container, or a way to resume after interruption. In other words, tool use is necessary for many agents, but it is not sufficient. A single prompt can produce a tool call, the host can execute it, and the model can see the result, yet the whole exchange can still evaporate at the end of the run. That is still closer to an augmented completion than to an operational agent. The distinction becomes obvious in the Atlas Travel Assistant. In a plain chat exchange, Atlas can answer a travel question, perhaps even search the web, or calculate a conversion if the model is allowed to call tools. But once the response is delivered, the system has no machine-readable record of where it left off unless the application explicitly preserves that information. If the user returns later and asks, "Now compare that itinerary with a cheaper option," the model may need the full story repeated unless the host has built a runtime that remembers what happened, what was retrieved, and what is still pending. Agency begins when the system can continue a task across turns without pretending each turn is the whole task. Figure 1.5. Stateless tool use ends after a response, while a persistent agent runtime preserves state, tool observations, and thread identity, so the task can resume later. That is why bounded autonomy matters here. Many readers first encounter tool use through a chat interface and mentally collapse three different things into one: the model's ability to propose an action, the host's ability to execute it, and the runtime's ability to preserve the task across steps. Those are separate layers. A chat UI can expose tool use, but if it lacks a persistent execution substrate, it is still an interactive session rather than an agent runtime. The difference is not philosophical. It is operational. A system that cannot resume, branch, inspect, or reliably continue from a save point is difficult to debug, hard to govern, and fragile under interruption. Read the structure first, then trace how each line carries the idea forward. Read the structure first, then trace how each line carries the idea forward. Read the structure first, then trace how each line carries the idea forward. These three snippets define the baseline and also the limit of the baseline. The first is a pure stateless call. A prompt enters, text leaves, and the process ends with no durable execution context. The second defines tools in their schema, which is enough for the model to name an action and enough for the host to execute it, but still not enough to make the overall system persistent. The third binds those tools to the model so that generation can include structured tool requests. That binding is important because it converts tool use from an external orchestration hack into a first-class output mode. Yet the runtime still remains single run unless the application itself keeps track of what happened. A useful way to think about the misconception is that many systems stop at the model can act. Agents require the further capability. The system can continue acting with memory of what just happened. That second clause is the real boundary. A tool-bound model can request a search, but if the result is lost when the call returns, the system has not learned anything operationally. A genuine agentic system needs a persistent loop around the model so that action, observation, and continuation are part of the same execution process. Without that loop, the tool call is just an isolated event. The stateless loop as a host-managed execution cycle. The smallest useful bridge from tool access to agentic behavior is a host-managed loop. In this pattern, the host application owns the execution cycle. It creates the message list, invokes the model, inspects whether the model requested a tool, executes that tool outside the model, appends the result, and repeats until the model stops asking for tools or the step budget is exhausted. The loop is simple, but simplicity hides an important design truth. The model is not controlling the world directly. It is negotiating with the host, one turn at a time, through structured outputs. The host is therefore not a passive transport layer. It is the runtime supervisor for the entire conversation. It decides how many steps are allowed, how tool outputs are represented, and what should happen when the model keeps asking for more actions. That final wrap-up prompt in the code is not an implementation curiosity. It is a termination guard. An open-ended tool-using model can easily continue requesting retrieval, calculation, or refinement indefinitely unless the host imposes a stopping rule. A bounded agent is not one that never wants to continue. It is one that has an explicit limit and a predictable exit path. Read the structure first, then trace how each line carries the idea forward. Read this loop as a relay race rather than as a single uninterrupted thought process. The model runs one leg and hands the baton to the host whenever it emits a tool call. The host runs the external action, converts the result into a message, and hands the baton back to the model. The model then sees new evidence and chooses the next move. That is the essence of the reasoning action feedback loop in operational form. There is nothing mystical here. The loop is a control structure, and the control structure is what gives the interaction temporal shape. The step budget is particularly important because it reveals that tool access alone does not create self-regulating behavior. An unrestricted tool loop can be functionally infinite even when each individual step is well-formed. In practice, every production agent needs some combination of maximum steps, budget limits, or explicit stopping conditions. The host can also decide whether multiple tool calls are allowed in one iteration, whether they are executed sequentially or in parallel, and whether partial failures should stop the run or route the system into a recovery branch. Even in this minimal example, the host has already become the policy center for execution. The final wrap-up prompt is a pragmatic stopgap, not a substitute for a fuller control flow model. It works because it forces the model to produce a concluding response after the loop has reached its ceiling. This pattern is useful in didactic code and in constrained systems, but it also illustrates a larger design principle. If you want autonomy, you still need a boundary. Bounded autonomy is not a reduction of capability. It is the mechanism that makes capability usable in real software. separating model output, tool execution, and observations. A common source of confusion is to speak about a tool using model as though the model itself performed the search or calculation. That language is convenient, but technically sloppy. The model emits a structured request. The host executes the request. The host then injects the resulting observation back into the message sequence, so the model can condition its next generation on the fresh evidence. That separation matters because it defines where trust, errors, and side effects live. The model proposes, the host disposes. The model reasons over the outcome. The host makes the outcome happen. This division is what makes agentic loops inspectable. If Atlas asks for an internet search, the tool invocation is not hidden in a black box. It appears as an explicit execution event. If the calculator returns a numeric value, that value is appended as a tool message, not silently folded into latent state. If the result is wrong or stale, the trace can show whether the error came from the model's request, the tool implementation, or the host's message handling. The quality of the overall system depends on preserving that boundary instead of letting execution details leak into the model's internal reasoning or, worse, disappearing entirely. The mechanism is deceptively simple. Tool results are turned into messages, and messages are the substrate that the model can consume on the next turn. In effect, the host writes the environment back into the conversation. This is why the format of the observation matters. If the tool result is too verbose, the model can be distracted or overwhelmed. If it is too terse, the model may lose the nuance needed for the next decision. If it is malformed, the model may misread the evidence or ignore it. A well-designed tool loop treats observation injection as part of the interface contract, not as incidental plumbing. There's also a subtle but important distinction between what the model sees and what the system knows. The model only sees what the host injects into the message sequence. The host, however, may retain richer execution metadata, timing, errors, and routing state. That means the same run can have multiple layers of evidence. The assistant message is the model's output. The tool message is the environment's response. The trace is the runtime's record of the exchange. Confusing these layers makes debugging much harder, especially once the system starts branching or persisting state across turns. The Atlas example makes the point cleanly. Suppose Atlas searches for current flight availability and then uses the calculator to compare total costs. The model may generate the plan, but the host performs the search, the host performs the calculation, and the host reintroduces those outcomes as observations. Later, the model can summarize the best option because it has seen the tool outputs in the same message sequence. Without that injection step, the model would be reasoning in the dark. With it, the system behaves as a closed loop rather than a one-shot guess. Shared state turns a loop into a workflow. A loop becomes a workflow when the runtime gives the steps a shared, named state object. In the stateless example, the messages live in a local list inside the function. That works for a single run because the function owns the whole story. It does not work for persistence because the list disappears when the function returns. A stateful workflow externalizes that list into a structured state container, usually with additional control fields that describe where the execution should go next. That is the difference between an ephemeral procedure and an inspectable runtime. In practice, shared state should carry more than raw dialogue. It may contain accumulated messages, intermediate decisions, routing hints, tool outputs, and other machine-readable fields that influence later steps. The key idea is not merely store chat history. The key idea is store execution state. Chat history is only one component of that state. If you store only human and assistant text, you may preserve the transcript but still lose the control information that lets the runtime resume meaningfully. A checkpoint agent needs enough structure to understand both what was said and what the system was doing when it paused. This is where @_messages is worth reading as a merge policy rather than as a convenience helper. In the graph example, the state field for messages is annotated so that new messages are merged into the existing sequence instead of replacing it wholesale. That is a subtle but decisive semantic choice. Replacement would make each node responsible for reconstructing the whole conversation state every time. Merge lets each node contribute only its delta. In a persistent execution system, deltas are what you want because they make resumption, tracing, and branch comparison tractable. Read the structure first, then trace how each line carries the idea forward. The graph makes the control structure explicit. The LLM node is responsible for generating the next candidate action. The tool node is responsible for performing tool calls. The routing function is the guard that decides whether execution stops or cycles back. In a flat loop, this logic exists implicitly in the host code. In a graph, it becomes part of the execution model itself. That shift may seem cosmetic at first, but it fundamentally changes how the system is reasoned about. A graph can be inspected, compiled, checkpoint, and resumed in ways that an ad hoc loop often cannot. Figure 1.6. A host-managed loop turns tool use into an agentic control cycle by alternating generation, tool execution, and observation until a stopping condition is reached. The Atlas workflow can now be described precisely. The state holds the current messages. The LLM node reads the messages and emits either a direct answer or a tool request. The routing function examines the last message and checks whether any tool calls were produced. If tool calls exist, the graph transitions to the tool node, otherwise it ends. After the tool node appends the observation, the graph transitions back to the LLM node. The loop is still there, but it is no longer hidden inside control flow conventions or local variables. It has become a first-class structure. This is also where hierarchical state machines become relevant, even before the reader studies them formally. A graph with a single cycle is already clearer than a hidden while loop, but real systems often need nested behavior. A support triage agent might route from a top-level intake stage into a subgraph for policy lookup or escalation. A travel planner might route from research into booking into approval. The hierarchical idea is that a parent state machine can hand off control to a subgraph while keeping the larger execution context intact. Even in this chapter, the important lesson is that shared state gives you a place to store that context without forcing every step to be monolithic. Checkpointing versus tracing. Persistence is not observability. Once the execution is stateful, two different forms of inspection become essential, and they are easy to confuse if the runtime is new to you. Checkpointing is about saving the machine-readable state so execution can resume later. Tracing is about recording what happened so the run can be inspected afterward. A checkpoint is a pause button for a specific execution lane. A trace is the dashboard recorder that shows how that lane moved. Both are useful, but they answer different questions. A checkpoint restores the runtime. If Atlas is interrupted after searching for flights, but before writing the final recommendation, a checkpoint can bring back the messages, the routing position, and any queued execution metadata needed to continue. A trace does not do that. A trace tells you that the model requested the search tool returned data, and the LLM node responded afterward, but it is not itself the live state of the agent. Thinking of a trace as memory is a category error. It is an observability artifact, not an execution substrate. The distinction matters most when the system misbehaves. Suppose the model repeatedly calls the calculator because a tool observation is malformed. The trace will let you see the repeated loop, the tool requests, and the node transitions. The checkpoint will let you resume from the saved state after you correct the bug or intervene manually. One artifact is diagnostic. The other is operational. In a production environment, you often need both, because one tells you what happened and the other lets you continue from where it happened. Read the structure first, then trace how each line carries the idea forward. This tiny compilation step is where persistence enters the runtime. The graph itself describes behavior, but the compiled application knows how to persist and recover state for a particular thread. The in-memory saver is intentionally simple for teaching purposes, yet the underlying idea is general. The execution state is stored separately from the model call, and a thread identifier selects which state instance should be used. A checkpoint run is therefore not a loose collection of messages. It is a resumable record associated with a key. Tracing, by contrast, can exist even without checkpointing. You can observe a run through stream node updates, logging, and message formatting even if the system discards state at the end. But once you add checkpointing, tracing becomes dramatically more valuable because you can compare what the runtime thinks is stored with what actually flowed through the nodes. That comparison is often the fastest way to catch a mismatch between intended control flow and actual behavior. For that reason, persistent agent systems should be designed with both restoration and inspection in mind from the beginning. Thread IDs as execution boundaries. Thread IDs are the simplest practical boundary for persistence. They tell the runtime which saved execution lane to resume and which lane to keep separate. If you think of a thread as an execution branch, the analogy is useful but incomplete. A thread is not just a label on a conversation. It is the key that partitions the save state space. Two runs with different thread IDs can share the same graph, the same model, and the same tools while maintaining completely separate histories and checkpoints. That separation is crucial for both correctness and reproducibility. In Atlas, a user may start one travel planning thread for a July trip to Tokyo and another for a December trip to Lisbon. The same agent logic can handle both, but the persisted state must not bleed across them. If the runtime merged the branches unintentionally, the assistant could reuse stale facts, cross-wire tool results, or answer from the wrong context. Thread IDs prevent that by making the persistence boundary explicit. The same mechanism also enables replay. Because a thread key locates the checkpoint state, the system can resume from that state after an interruption or use it as the starting point for further experimentation. This is a subtle but powerful shift. The execution is no longer just what the model said last. It becomes a version trajectory that can be resumed, inspected, and, if necessary, duplicated into a separate branch. That is why persistent execution begins to feel more like version control for runtime behavior than like a chat transcript. Read the structure first, then trace how each line carries the idea forward. Reading and inspecting save state. Once state exists, developers need to inspect it without mentally expanding an entire conversation every time. The compact formatter above serves that purpose by turning each message into a short, one-line summary. This is more than a cosmetic convenience. When an execution graph accumulates multiple turns, tool calls, and observations, the raw message list becomes difficult to scan. A compact form makes the structure legible by emphasizing the role of each message and surfacing tool calls directly. Read the structure first, then trace how each line carries the idea forward. The snapshot printer is a debugging lens, not part of business logic. It reveals the current message count, the most recent messages, and any routing metadata, such as the next node or queued tasks. That visibility is essential because a persistent graph is not just about what the model says. It is also about what the runtime believes is pending. If the last message is a tool call and the next node is still the tool node, the snapshot explains why the system has not yet produced the final answer. If the next node is empty, the graph has probably reached termination. The practical value of compact formatting shows up when a run has several cycles. A raw state dump with repeated assistant outputs and tool messages quickly becomes noisy. By reducing each message to role plus essential content, you can see the execution pattern at a glance. That helps you answer questions such as whether a tool call was actually appended, whether the final assistant response was persisted, and whether a branch contains the expected divergence from the main path. Read the structure first, then trace how each line carries the idea forward. This streamed execution helper shows what tracing is for. It reveals node entry and exit, the fields updated by each node, and the brief shape of the most recent message after each update. Notice that it does not change the persistence model at all. It only observes it. That is the cleanest way to keep the roles distinct. State is what the runtime stores, tracing is what the developer sees, and the graph is the structure that connects the two. A two-turn continuation in the same thread. The first substantive test of a persistent runtime is whether a follow-up turn can reuse the prior turn's results without restating everything. In Atlas, that is the difference between a session and a memoryless script. If the first turn retrieves a temperature and the second turn asks for a transformation of that same temperature, the host should not require the user to repeat the numeric value manually. The thread's checkpoint state should carry the earlier result forward. Read the structure first, then trace how each line carries the idea forward. The first turn establishes the thread state. It may involve one or more tool calls before the model produces the final answer. But the key point is that the result is now associated with the thread ID. The trace makes the sequence visible, while the snapshot confirms that the messages are saved. This is the operational baseline for persistence. Read the structure first, then trace how each line carries the idea forward. The second turn is where the runtime proves its value. The prompt is intentionally incomplete if read in isolation, but in the same thread it is sufficient because the prior checkpoint fills in the missing continuity. The model can draw on the previously persisted messages and proceed as though the conversation were continuous, because from the runtime's perspective is continuous. That is the advantage of a stateful execution model over a stateless loop. Continuity is not reconstructed by hand every time. It is encoded in the runtime. A subtle but important implication follows. Continuation is not the same as long context. The system is not merely stuffing more text into the prompt window. It is retrieving a saved execution state that already knows what happened on earlier turns. That distinction matters when the conversation gets longer, when state must survive interruptions, and when the runtime needs to make routing decisions based on saved control data rather than on raw transcript length. Branching a conversation without overwriting the original. A persistent runtime becomes much more powerful when it can fork. Suppose Atlas has a saved conversation about a trip, and the user now wants to explore an alternate itinerary without disturbing the main plan. A separate thread ID creates exactly that effect. The new thread can start from the same conceptual past, but it develops independently. This is the practical meaning of branching: divergent futures without destructive overwrite. Read the structure first, then trace how each line carries the idea forward. In this branch, the runtime uses a different persistence key, so the conversation can evolve in a different direction. The host does not need to clone the whole application, and the model does not need a different prompt format. The only change is the execution lane. That is the same core pattern used in much more advanced settings later in the book, including replay, comparison, and evaluation. Here it serves a simpler purpose: preserving isolation while allowing divergence. Read the structure first, then trace how each line carries the idea forward. Comparing the saved snapshots is where the branching idea becomes unmistakable. Each thread retains its own message list and its own checkpoint execution history. The main path preserves the original line of work. The branch preserves the exploratory alternative. The two do not collide because persistence is keyed by thread identity, not by some global mutable conversation bucket. That difference seems small in code and enormous in practice. This is also the point where many engineers realize that persistent execution is closer to version state than to a transcript. A transcript is a linear diary of words. A checkpoint thread is a saved machine state that can be resumed, forked, or inspected after the fact. Once you see the runtime this way, it becomes easier to reason about the design choices that follow in later chapters, including handoffs, human approval gates, memory, and evaluation. They all build on the same underlying idea. Stateful execution is not a luxury feature. It is the substrate that makes an agent behave like a dependable system rather than a clever one-off call. What the example teaches about persistent agent runtimes. The progression from a stateless call to a tool-bound model, then to a manual loop, and finally to a compiled stateful graph is not just a sequence of implementation tricks. It is a conceptual ladder. At the bottom, the model predicts text. One rung up, it can request tools. Another rung up, the host can run a bounded reasoning action feedback cycle. At the next rung, the execution becomes graph-shaped, with explicit nodes, transitions, and guards. Above that, checkpointing and thread IDs make the process resumable and branchable. Each step adds a different kind of control, not just more code. For Atlas, that ladder is what turns a conversational assistant into a persistent planner. The same architecture can search, calculate, remember the latest state of the conversation, and resume after interruption. It can be traced when something looks odd. It can be resumed when a user comes back. It can be forked when a user wants to explore an alternative. None of those properties come from tool binding alone. They come from a runtime that wraps tool use in explicit control flow and persistent state. That is the conceptual boundary to keep in mind as the book moves forward. An agent is not merely an LLM with access to APIs. It is an LLM embedded in a stateful execution model that can decide, act, observe, and continue under clear limits. Once that boundary is internalized, the later discussions of planning, handoffs, interrupts, and hierarchical orchestration become much easier to place. They are refinements of the same substrate, not separate inventions. Autonomy is one of the most overloaded words in the agent conversation. In everyday product language, it often means a system can do something by itself, but that phrasing is too loose to be useful in engineering. A system can complete a task without being autonomous in any meaningful architectural sense, and a system can be highly autonomous within a tight envelope without resembling open-ended intelligence. The distinction matters because production systems are judged by whether they can make decisions, act, recover, and remain governable under real constraints. That is why autonomy needs a boundary condition. Without one, the word becomes marketing camouflage. The most useful boundary is not philosophical, but operational. A system is autonomous only to the extent that it can choose among permitted actions while remaining inside a predefined control structure. That control structure may include states, transitions, tool permissions, retry rules, approval gates, and supervision policies. Anything beyond that is not autonomy in the agentic system sense used in this book. It is either a different system design or a claim that has not yet been demonstrated. The practical question is therefore not whether a system acts on its own in the abstract, but what authority it has at runtime, what it is allowed to vary, and what remains fixed regardless of its behavior. That framing makes autonomy measurable rather than mystical. A useful analogy is a control room rather than a self-governing organism. In a control room, operators can reroute power, divert traffic, or adjust thresholds because the system exposes levers and feedback channels. They do not, however, redesign the building while the building is running. Agentic software is similar. It can be powerful precisely because it can select among controlled paths, invoke tools, and react to state changes. It is not powerful because it invents new roads, creates new governance structures, or rewrites its own operating model in production. This difference is subtle in demos and decisive in deployment. A model that can decide whether to search, calculate, summarize, escalate, or stop is exhibiting useful autonomy. A model that can rewrite the graph that governs those decisions would be operating in a different category entirely, and current systems do not reliably reach that category. This figure illustrates bounded autonomy. The agent can choose among permitted actions inside a governed envelope, while the control structure itself remains fixed and externally owned. The envelope defines what actions are allowed, what tools are available, and what states are reachable. Everything outside that envelope is off-limits. This is the key idea. The agent has freedom within a cage, and the cage is what makes the system auditable, safe, and debuggable. This figure illustrates bounded autonomy. The agent can choose among permitted actions inside a governed envelope, while the control structure itself remains fixed and externally owned. The envelope defines what actions are allowed, what tools are available, and what states are reachable. Everything outside that envelope is off-limits. This is the key idea. The agent has freedom within a cage, and the cage is what makes the system auditable, safe, and debuggable. This is also why the most honest framing is not, does it have autonomy, but how much autonomy has been intentionally granted. Bounded autonomy is not a concession made to current model weakness. It is a design choice that turns raw model capability into a deployable system. A bounded system is auditable because its choices are made from a known menu. It is safer because dangerous actions can be isolated behind permissions and interrupts. It is easier to debug because state transitions can be observed and replayed. The boundary is therefore not a limitation to apologize for. It is the mechanism that makes the system real enough to trust. Orchestrated autonomy is a specific kind of autonomy, one that only exists inside a carefully defined contract. The contract spells out the states the system can be in, the transitions it can take, the tools it can use, and the safeguards that limit its actions. By the end of this part, you'll understand how this contract shapes what the system can and cannot do. The contract defines everything. If the system has to ask for permission before proceeding, that's part of the contract. If it can only choose from approved branches, that's part of the contract too. Even inspecting external data without being allowed to change sensitive records, that's also in the contract. The model isn't an unrestricted agent. It's a participant in a controlled workflow whose authority has already been engineered. This distinction separates freedom of choice from freedom of structure. At runtime, the system can pick which approved path to follow, which tool to call, which subtask to prioritize, or whether to request escalation. What it cannot do is redefine the graph itself. The graph topology, the tool registry, the safety policy, and the approval conditions are external commitments. The model operates within them, but does not own them. Its intelligence shows as controlled selection, not architectural sovereignty. That's why finite state machine and hierarchical state machine language remains so valuable. An orchestrated system can be described as a machine that occupies a state, receives observations, and transitions along edges whose conditions are known in advance. The machine may be sophisticated, its states hierarchical, its local decisions data-dependent, but the overall control contract stays explicit. A superstate defines a bounded region of behavior with internal substates for planning, acting, reflecting, and retrying, yet the set of permissible moves remains finite and supervised. That's the essence. Deliberate control shaped to support adaptation without surrendering governance. The design contract also clarifies why human-in-the-loop is not a synonym for weakness. In an orchestrated system, human involvement can be part of the normal authority model. A sensitive action may require approval, not because the machine failed, but because the workflow was designed to reserve final authority for a person. A branch may pause for review because the system reached a confidence threshold or the risk profile changed. In both cases, supervision is not an interruption of autonomy. It's a boundary inside autonomy. The system can move, but only where movement has been authorized. Autonomy in agents is best understood as a ladder of control authority, not a simple yes or no label. Each rung represents a different level of decision-making power, but all operate within a fixed, supervised structure. At the lowest rung, the system acts like a router. It doesn't deliberate endlessly. It classifies a request, selects a policy branch, or dispatches a message to a specialist workflow. The choice is made at runtime based on current state, not hard-coded as a single linear path. In practice, this is a tiny finite state machine. One decision point, a guarded transition, and a fixed set of destinations. This figure shows the capability ladder. Notice how each rung, from router to tool calling agent to multi-agent system, adds more decision points and loops, but the entire structure remains inside a governed envelope. The boundaries are fixed. Only the depth of control authority increases. The next rung is the tool calling agent. Here the system enters a repeated loop. It plans, acts, observes, and revises. It might call a search tool, inspect the result, use a calculator, update its internal state, then decide whether to continue or stop. This feels much more agentic because the system manages a sequence of bounded decisions over time. But the loop exists because the designer created it. The model chooses among available actions, but does not invent a new control regime while running. A multi-agent system raises the apparent level of independence. A supervisor routes work to sub-agents, each with a narrower specialty. One researches, another verifies, a third drafts. Coordination can happen sequentially or in parallel, and the system looks far more sophisticated than a single prompt response exchange. But sophistication is not open-ended autonomy. The complexity comes from orchestration depth, not from a loss of boundaries. The useful way to read the latter is not weak to strong intelligence, but narrow to broader control authority within a governed envelope. This prevents the mistake of assuming that any system with loops, memory, or delegation has become independently self-directed. The system may have more options, more depth, and more internal coordination, but the options remain curated, the depth remains structured, and the coordination remains supervised. That is enough to make the system useful and to keep the terminology honest. FSM and HSM language gives us a clean way to see why different agent patterns feel distinct while still belonging to the same design family. A router is the simplest case. It's like a minimal FSM with one guarded branch. The state is the current request and a bit of context. The transition is a classification or routing decision. The output is the next workflow stage. Little hidden behavior is exactly why routers are so useful in production. Smaller machines are easier to test, log, and debug. A tool calling agent fits better as a hierarchical machine. Instead of a flat collection of states, it has a working region that contains repeated cycles of planning, action, and reflection. That working region is a superstate. While the machine stays inside it, it can move among substates without leaving the broader contract. The hierarchy reduces transition explosion. Without it, every state would need explicit transitions to every possible next state. With hierarchy, common behavior is factored into shared structure, keeping the machine comprehensible even as behavior gets more nuanced. Multi-agent systems can be read as a machine of machines. The supervisor occupies a higher-level state that decides which subgraph should run, whether multiple subgraphs should proceed in parallel, and when results should be merged or escalated. Each subagent is its own bounded machine, but the system as a whole has an additional orchestration layer. AMAS is not a break from FSM/HSM thinking. It's an expansion. The machine is now hierarchical not only inside one agent, but across a collection of agents. This perspective has a practical payoff because it changes how you evaluate claims. When a vendor says a system is autonomous, the real question is not whether it has a loop. It's where the loop sits in the state hierarchy, who controls the transitions, and which transitions are irrevocably fixed by design. A router is not a weak agent, and a multi-agent system is not a strong one just because it contains more model calls. The difference lies in control structure, not in branding. Once you learn to read agents through FSM and HSM language, hype becomes much easier to filter. This perspective has a practical payoff because it changes how you evaluate claims. When a vendor says a system is autonomous, the real question is not whether it has a loop. It's where the loop sits in the state hierarchy, who controls the transitions, and which transitions are irrevocably fixed by design. A router is not a weak agent, and a multi-agent system is not a strong one just because it contains more model calls. The difference lies in control structure, not in branding. Once you learn to read agents through FSM and HSM language, hype becomes much easier to filter. A system can adapt at runtime without changing its own architecture. That is the key distinction in this part. Adaptation within a fixed structure versus rewriting the structure itself. Current agent systems can adapt in meaningful ways. They can select one branch over another, choose among tools, revise a prompt, ask for clarification, decide to stop early, or delegate a subtask to a specialist. They also react to changing observations like failed tool calls, missing information, or contradictory evidence. This is real adaptability, and it is why agentic workflows are more powerful than static scripts. What they cannot do reliably is rewrite the control system that enables that adaptability. They do not spontaneously invent a new graph topology, validate it as safe, deploy it, and prove its rules align with the original goal. That is a much stronger claim than choosing among allowed transitions. A system may optimize the path it takes through the graph, but it does so within a graph someone else defined. The path can vary. The roads are fixed. Consider an Atlas travel assistant that receives a request. It can answer from memory, from search, or by asking a clarification question. At runtime, it chooses based on confidence, policy, or cost. It may also revise its working prompt by reformatting context to emphasize constraints, not by changing the architecture. These are examples of controlled adaptation, not self-re-engineering. The model works inside a living system that gives it room to react without rewriting the rules. That distinction clarifies why thread local state and checkpoints matter. A runtime branch can be explored, abandoned, or resumed because the system records what happened without making every decision permanent. A divergent thread can test an alternative interpretation while preserving the original execution. This supports robust orchestration without conferring limitless freedom. The system varies execution while the framework keeps authority boundaries intact. That is the sweet spot. Enough adaptivity to handle uncertainty, enough structure to preserve control. Bounded autonomy solves problems that static pipelines and unconstrained generation both handle poorly. Static pipelines are reliable only when the path is known in advance, and plain model calls can't sustain multi-step tasks across tools. Bounded autonomy sits between those extremes, giving the system enough freedom to respond while keeping structure for safety and auditability. This combination is especially valuable where failure needs to be contained, not just avoided. A travel assistant can compare options, call approved tools, ask for approval before a risky purchase, and preserve state for follow-up. A support orchestrator can classify a ticket, retrieve policy, draft a response, and escalate when confidence drops. A research agent can explore hypotheses without silently altering success criteria. In each case, bounded autonomy turns a fragile prompt into a governed operational process. There's also a less obvious benefit. Bounded autonomy improves explainability without requiring the system to be simple. When control is explicit, you can see why a branch was taken, what tool was called, which state changed, and where human review entered. That makes the system more trustworthy than a black box loop that just seems to work. The point isn't that bounded systems are perfect, it's that they fail in ways you can inspect, contain, and iterate on. In production, that's often the difference between a useful agent and an unsafe demo. That inspectability is what makes bounded autonomy practical for production. You can see the decision path, the tool calls, the state changes, and where human review is needed. It's not about perfection. It's about having failures you can understand and fix. That's the difference between a useful agent and an unsafe demo. AI Scientist V2 is a concrete example of what orchestrated autonomy can achieve today. It is a multi-agent research workflow that moves through a scientific pipeline, proposing hypotheses, writing code, running experiments, debugging failures, visualizing results, and assembling a manuscript draft. The key is that bounded autonomy is not limited to trivial tasks. Within its envelope, this system coordinates a surprisingly rich research process. What makes AI Scientist V2 interesting is not any single step, but the continuity across them. In a research workflow, static automation usually breaks down because each stage depends on the outcome of the previous one. Hypothesis generation changes what code to write, experimental failures change what needs debugging, and visualizations change what the manuscript should emphasize. This system preserves state across the workflow, allowing each stage to feed the next. It behaves less like a prompt response system and more like a research factory with bounded roles, checkpoints, and handoffs. Parallel execution makes the system even more capable. It can run multiple experiments concurrently, compare results, and refine based on what comes back. That is a meaningful increase in control authority because the system is no longer reacting serially to one result at a time. It is coordinating a small portfolio of actions. Yet the parallelism does not change the fundamental character of the system. It still operates within a preset process for proposing, testing, debugging, and writing. The machinery is intricate, but it is still machinery. The concrete outcome here is a workshop-level acceptance that demonstrates that bounded autonomy can produce work that clears a real review process, not just a synthetic benchmark. It validates the engineering premise of the whole chapter. When state, tools, and control flow are assembled well, an LLM-based system can do more than chat. It can execute a real work loop with outputs that matter to other humans. The value of this case study lies in its boundary, not just its success. It shows how far orchestrated autonomy can go today without pretending it has crossed into open-ended scientific agency. The system can contribute to research-like output, but it cannot be treated as a fully independent scientist. The value of this case study lies in its boundary, not just its success. It shows how far orchestrated autonomy can go today without pretending it has crossed into open-ended scientific agency. The system can contribute to research-like output, but it cannot be treated as a fully independent scientist. The case study of AI scientist V2 is compelling precisely because its limitations are visible. It shows us where bounded autonomy hits a ceiling, and that ceiling is what we need to understand. The system can do substantial work, but the quality is uneven. Shallow analysis appears when the workflow follows the surface structure of research without achieving deeper insight. Methodological gaps show up when experimental design isn't rigorous enough. Citation errors remind us that fluent composition is not scholarly reliability, and weak novelty is the most important limitation. Scientific value depends on contributing something meaningfully new, not just producing a plausible artifact. These failures are not accidental side effects of a few buggy components. They're symptoms of the current boundary of bounded autonomy itself. The system can coordinate steps, but coordination is not judgment. It can run experiments, but it cannot guarantee the experiments ask the right question. It can draft a manuscript, but drafting is not peer review. The architecture is strong at execution within a bounded loop, but weaker at guaranteeing the epistemic quality of what that loop produces. That is why human oversight remains essential even when the system is productive. A scientist, engineer, or reviewer must still evaluate whether the hypothesis is interesting, whether the experimental design is fair, whether the citations are correct, and whether the contribution is actually novel. The agent can assist with labor, acceleration, and iteration, but cannot be the final arbiter of rigor. This is the natural consequence of bounded autonomy. The machine is powerful inside its scope, not sovereign over the standards that define success. The broader lesson is that capability should not be confused with autonomy. A system can appear remarkably capable because it completes a long task chain, yet still remain tightly bounded in the decisions it is allowed to make. The example cuts both ways. Current systems are already useful enough to change how research is done, and they still need human judgment to avoid shallow, brittle, or misleading results. That dual message is the honest reading of present-day agentic systems. Oversight is not a temporary crutch for a system that hasn't reached full autonomy. In production agent design, it is a structural part of the autonomy model itself. A common mistake is to treat human oversight as something that will disappear once the system becomes fully autonomous. That framing is misleading. Approval gates, interrupts, review points, and escalation paths are not signs that the architecture fell short. They are the destination. The system was designed to operate with distributed authority, where some decisions stay machine-led and others remain human-controlled. This matters most when the cost of a wrong action exceeds the value of extra automation. Research integrity, financial commitments, policy compliance, safety, and high-stakes customer actions all benefit from a workflow that proceeds automatically up to the point where human judgment is necessary. Oversight increases trust because it limits the blast radius of errors. It also makes accountability boundaries legible, which operators can actually use. Seen this way, supervised autonomy is not a compromise between automation and control. It is an intentional synthesis of both. The system is useful, adaptive, and persistent, but it never becomes an unaccountable actor. The control room analogy matters here. The operator is not there because the machine is too weak to function. The operator is there because the machine is powerful enough that its actions must remain governable. When someone claims a system is autonomous, you need a consistent way to test that claim. This diagnostic framework gives you a reusable set of questions to evaluate any agent architecture. Start by identifying what is fixed in the system, what the system can choose at runtime, and what remains under human control. If the control graph is fixed, but the system can choose among branches, that is orchestrated autonomy. If the system can also call approved tools and revise its next step context, the autonomy is deeper but still bounded. When multiple bounded subagents are coordinated by a supervisor, the system is more complex but still within the same family. The label may change, but the diagnostic remains the same. The next question is whether the system can only vary execution or whether it can alter the structure that governs execution. This is the line that marketing often tries to blur. A system that loops over tools is not automatically autonomous in the stronger sense. A system that delegates work is not self-governing by virtue of delegation alone. A system that completes a long task chain is not redesigning itself, unless it can actually modify and validate the control structure that governs its own behavior. In current practice, that second claim is rarely justified. A final diagnostic is to ask what the human still owns. If the human owns the graph design, the tool permissions, the approval rules, the evaluation criteria, or the final judgment, then the system is best understood as orchestrated autonomy rather than open-ended autonomy. That is not a downgrade. It is the correct description of a system that is strong enough to help and constrained enough to trust. The ability to choose within a fixed graph is already valuable. The ability to design the graph itself is a different problem, and today's systems do not solve it reliably. This diagnostic lens is the one to carry forward. It prevents inflated claims, keeps the vocabulary precise, and makes future architectures easier to compare. A good agent is not the one that sounds the most independent. A good agent is the one whose authority is clear, whose behavior is bounded, and whose runtime choices are powerful enough to be useful without escaping the contract that makes the system safe to operate.